Well, hello. Welcome to Physical Science for today. And today's topic that we're going to be discussing is going to be related to forces. Okay, and we've been kind of dancing around this idea a little bit. They've been lurking in a lot of the things that we've been doing because we've been talking about motion. The reason why motion occurs is usually because of something to do with force, either the presence of a force or a lack of a force. And so let's first define what a force is. And it's pretty much what you know. A force is a push or pull. I can push on something, I can pull on something. Those are forces. Now, back in the 1600s, a rather sharp fellow by the name of Isaac Newton came to understand that forces are going to relate to motion, and he was able to kind of determine a couple key things, and some of them were not so obvious as they might seem to us now, because we kind of use these terms quite frequently. You've heard what these laws of motion are, and so these are Isaac Newton's laws of motion. Okay, and there are three laws of motion, and you can either take notes on this or they will be available on a sheet that you're going to be doing, so you have easy reference to it. But let's kind of distinguish what these laws of motion are. Now, the first of these is sometimes called the law of inertia. If something has inertia, it doesn't want to change what it's doing. Okay, think of it as being a very kind of almost a stubbornness of an object. So what the law of inertia states is that an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Both objects are going to try to do what they're doing. So if I don't exert any outside force on an object at rest, it's going to stay at rest. And this makes perfect sense. You guys are probably thinking, like, why would we even need to say that? But it's the second part of this that we have a tough time grasping. Because if an object is in motion, here on Earth we don't oftentimes see it stay in motion. The example they give is a ball rolling on the grass. Okay, it's eventually going to come to a stop. But that's because there's an unbalanced force acting upon it. And that force is going to be the friction of the grass. But if there is no unbalanced force acting upon it, this object would move on forever. And the only place where we can eliminate friction normally is if we travel to outer space. And there you see this acting quite a bit. You see the planets, they are going to keep revolving around the sun. They're not going to stop. There's going to be no friction to stop them. Okay, so if I send out a space probe, it's going to head out to outer space. So that's Newton's first law of motion. Okay, an object in motion is going to stay in motion. An object at rest is going to stay at rest unless acted upon by an unbalanced force. Newton's second law of motion says that my net force equals the acceleration times the mass. Okay, so if I take a bat and swing a smaller mass baseball, it's going to accelerate more than if I take a bat and swing and hit a higher mass bowling ball. And so that can be written as force equals mass times acceleration. This is basically, if you know this equation, you know Newton's second law. And that is if forces are unbalanced. Right now, the force of the bat on the ball is an unbalanced force. The ball just wants to sit there, but the person hitting it applies an unbalanced force. You multiply the mass of the baseball times its acceleration, you can figure out the net force. Here, you multiply the mass of the bowling ball times its acceleration, you get the net force. We could have the same net force between these two bats, but the bowling ball is going to accelerate a lot less because it has much more mass. So those are Newton's second laws of motion right there. The third law of motion says that for every action force, there's an equal and opposite reaction force. And my guess is that you've heard this somehow. So if I've got two skateboarders and the person in green pushes against the person in yellow here, okay, it's not just the person in yellow that moves. The person in green moves as well because the person in yellow exerts an equal and opposite reaction force. Okay, so that is going to be Newton's three laws of motion. If I hit a nail with a hammer, the nail hits back equally as hard on the hammer. If I get mad and kick a wall because I'm angry, okay, I kick the wall, that's great, but the wall kicks back at me with an equal amount of force, and that's why my foot's going to hurt. So that'll teach me a lesson. So we did a lab where we were dropping some objects the other day, and those objects had a mass, okay? And we know that mass is going to stay the same no matter where I am in the universe. But the force of gravity is going to cause an acceleration. So what I have here, my weight is going to equal the mass times an acceleration. That is Newton's second law of motion. You might not realize it, but the reason why you have weight is because Newton's second law of motion. You have a mass, there's an acceleration due to gravity, and therefore you have a weight. Now, on Earth, the acceleration due to gravity is 9.8 meters per second squared. So 10 kilograms times 9.8 meters per second squared equals 98 newtons. Now on the moon is much smaller. It has less mass. It's going to have a lower gravity. So my acceleration on the moon, I'm going to take my mass. The acceleration due to gravity on the moon is only 1.6 meters per second squared. And so I'll find out that my weight on the moon is 16 newtons. But look at this. This right here is basically mass times acceleration. And that's going to equal my force, which is a weight. Okay? So 60 newtons on the moon, 98 newtons on Earth. And that is Newton's second law of motion. Now, we also had a lab yesterday that dealt with a balloon. And before we release the balloon and we're just holding it there, let's imagine that this air isn't coming out of it, that balloon is staying motionless. So initially, before we started releasing it, that would have been Newton's first law of motion. Okay? But as soon as I released it, there was an unbalanced force of the air pushing on the balloon, and it accelerated. So when it started to accelerate, that was Newton's second law of motion. Now, the reason why the balloon even moved in the first place was because of Newton's third law of motion. Just as the balloon was pushing on the air was pushing on the balloon. It was an equal and opposite reaction force, which is what allowed it to move. Now, once it got moving, it kind of went at a steady speed, which meant that the forces of friction and the forces of the air in the balloon were about balanced, because if it's moving at a constant speed, that's Newton's first law again. Okay? That would have happened at about the middle of your trip. But then, as air began to run out, friction began to slow it down. Friction was an unbalanced force, so that would have been Newton's second law of motion again. So you see in that simple little balloon lab we did yesterday, which is why we did it, we had all three types of motion, or all three laws of motion, that were all there at once. So here's what you're going to do for a lab today. I have a situation. So here on today's sheet, on today's assignment, you're going to see that I've got the laws written out there, and I have some examples here of each of those situations. So Newton's first law of motion, a soccer ball is going to stay seated unless an unbalanced force acted upon it. If an unbalanced force acts upon it, that would actually be Newton's second law of motion, so it would accelerate. But once it's in motion, it's going to try to continue in motion unless it's acted upon by an unbalanced force. So this would technically be first law of motion, second law of motion, first law of motion, second law of motion. Now, down here, you see Newton's second law of motion kind of written out as F equals ma, force equals mass times acceleration. Here I've got a small mass, so I'm going to have a large acceleration. Here I've got a larger mass, so I've got a smaller acceleration. Okay? So that is Newton's second law of motion. Force equals mass times acceleration. And the reason why this isn't Newton's first law is because this is an unbalanced force. This force is not counterbalanced by any opposing force. There's nobody pulling this wagon the other direction. And Newton's third law of motion says for every action force there's going to be an equal and opposite reaction force. So if I'm trying to walk to a dock here and I'm on a boat, if I try to push off the boat, okay, the boat pushes off me as well. So there's an action force and a reaction force. So I end up really not going anywhere, and I'm going to plunge right into the water if I'm not careful. So these are the Newton's 3 laws of motion, and what I'm going to have you guys do is try these on some computer simulations and try to figure out which law of motion it's describing, and kind of think about what that means for us. Okay, so that is going to be your task today. We introduced Newton's laws of motion. Okay, we reviewed the balloon lab a little bit, and I want you, before you even start this simulation, I want you to watch this video, because that's going to just give you another take, another look at it in terms of Newton's laws of motion. And then I want you to try these computer simulations. If you could finish that and get that to me, that would be a great way to spend your Wednesday. Thank you for your time today. I hope you guys enjoy your 4 days off. Okay, we will talk to you later.